Hi everybody, Physics Ninja here. Today what we're going to do is look at a parallel LRC circuit. We're going to look specifically at the one I've drawn here. It has one component through each of the parallel branches. We have one branch with a resistor, an inductor, and a capacitor. At the end I'll substitute these values in here just to calculate our what the questions I'm asking you for. First question is, what is the resonant frequency of this circuit? Secondly, let's find the current through each of these components. What's the current through the resistor, through the capacitor, and in the inductor? The last part is, what is the current being supplied by this power supply, by the voltage source in this case? And is that current leading or lagging the voltage? So let's go ahead and set up our equations and I'll show you how to solve this problem. So the first thing I would do here is, let's maybe simplify this circuit over here. Let's call this maybe point A and point B. And basically what I do is just kind of redraw it, and we're going to simplify it a little bit. Okay, so what we're going to do is first draw, instead of a resistor, let's just represent it by a little box. And I'm going to call this the impedance, Z, of a resistor. Okay, and the impedance of the resistor, this one's pretty straightforward. It's simply just the value of the resistance. The next thing we have here is the inductor. And let's represent this by, again, another little box. And what I want to do now is represent this guy. And what is the impedance of this guy? Well, that's the impedance of an inductor. And if you go look in your book, you should find that it's often written as complex number I multiplied by omega, the angular frequency, and also the value of the inductor L. All right, our last bit is our capacitance. And again, we just simply represent it by another small little box. And again, the impedance now of the capacitive component, the impedance you can write as Z subscript C. And again, look that up in your textbook. Probably something you saw in your class is I omega C. All right, so now what we have is a pretty straightforward circuit. My first goal here, although I say find the resonant frequency, let's actually just find how I can simplify this circuit, right? And my goal at the end is to represent this more complicated circuit by a single impedance value. Let's call this Z total. Okay, how would you find what the equivalent total impedance of this circuit is? This is something you should know how to do, right? If these were all real resistors, it's the same rule that applies if you want to simplify it, even though you have kind of complex values here of impedance. It doesn't really matter. So all we want to do now is simply do like 1 over Z total. Since we're simplifying a network of parallel impedances, equals 1 over the impedance of my resistor plus 1 over the impedance of the inductor plus 1 over the impedance of my capacitor. What we do now is simply substitute our values for all three values of impedances and simplify this a little bit. So let's go on the next page and do this math. All right, so we're going to do a little bit of algebra now. We'll start substituting our values. So again, we have 1 over Z total. We just want to find what the magnitude of Z total is. We're just going to substitute our values. So we have 1 over R for here. For the impedance of the inductor, we have 1 over I omega L. And now we're going to have, for the capacitor, it's 1 over. But then again, the impedance of the capacitor is 1 divided. So at the end, this ends up being I omega C for this term. What we're going to do now is maybe bring this exponential, or this imaginary number here to the numerator. And if you do that, you simply have to switch the sign, right? So this here ends up being a minus I omega L and plus I omega C. And one of our last steps now, let's just kind of write this in a more compact form. We can factor out this imaginary term. And let me just kind of switch the order here, right? The omega C term first, and then I have minus 1 over omega L. And this is 1 divided by my total impedance, right? At the end, what we're really looking for is what is the magnitude of the total impedance. So what you have to do now is, again, if you have a complex number, let's take any complex number, A plus IB. And if you're looking for what the magnitude of that number is for any imaginary number, what you have to do is you have to square the real component, and you also have to square the imaginary component. So what we have here, this is our real component, right? This is the real part. And this whole term here in the bracket. This is the imaginary part. Oops. Imaginary. So what we have to do is, again, let's start maybe by finding 1 divided by at the end. Then you could just kind of flip that number that you're going to get. This is a little bit easier. So what you end up doing here is, again, you're going to have the square root, just like we have over here for a squared plus b squared, except now we have our real part, which is squared, and plus our imaginary part. And this should be omega c minus 1 over omega L. And you got to square this whole term. Okay, and the last thing we want, is not 1 divided by z total. We're really interested in z total. So at the end, what you have to do is just flip this. So let's go on the next page and do that. All right, what we're looking for here is z total. If I just write it like this, z total. Again, this is 1 divided by z total. So all you have to do is just flip that term. I'll just do some cutting and pasting here rather than rewriting the whole thing. Just do Control C and Control V over here. Move that over, and it's the exact same term. Okay, so this is really what the magnitude, and let's go ahead and just make sure we have, this is the magnitude of the total impedance of my circuit. And the reason you want to know that is because, again, we've represented it now by this guy right here, right? We've had 3 different branches that we've simplified into a single branch. And what that means now is I can use this in order to find what is going to be the maximum current, right? There's going to be 2 things that this complex impedance does. First of all, if there's high impedance, it means that the current is going to be small, and it will also introduce an angle between our voltage source and our total current. Okay, so what we're going to first do is, let's see how you would calculate the maximum current. Okay, and for this, it's kind of just like using Ohm's law, right? All we're doing is either you take the peak voltage or the RMS voltage. Let's talk about the peak for now. Oops. If I was going to write the peak voltage I would write as the magnitude of the total impedance multiplied by the peak value of the current. Okay, the peak voltage I can find in this problem because I've given you what the RMS voltage, and that's kind of easy to do. At the end, what we're looking for is what is the peak current or the RMS current. Okay, so all you would have to do then is simply say that the peak current is equal to the peak voltage and divided by the magnitude of this total impedance. Okay, well, let's have a look at what happens at this total impedance for different values of omega, right? You could see that the omega terms end up coming over here, right? And there's one specific value of omega where this whole term over here actually goes to 0, and it no longer contributes to the total impedance. So let's go ahead and look more at this expression over here and see if we can find what the resonant frequency of this circuit is. So we first want to look at what happens when this term over here goes to 0. And that's going to happen when our value of omega c minus 1 over omega L equals to 0. Okay, so to do a little bit of math, you simply have omega c equals 1 over omega L. Now you can group the omega terms together, and you bring the c at the bottom. So this looks like omega squared equals 1 over LC. And this should look like a familiar result to you, right? At the end, what we're really interested in, what is that angular frequency? So you take the square root on each side, and I'll just call this res. Okay, so this is actually a really, really important frequency for this particular circuit, because it means that at this frequency, this is actually the resonant frequency of this LRC circuit. And it looks exactly like the value you did if you did an LRC circuit where all the elements were in series with each other. Okay, so this is their resonant frequency. So what happens at the resonant frequency? Well, at the resonant frequency, again, all of this bracket here will end up going to 0, right? That's what we have. That's our condition at the resonant frequency. And what you're left with is that the total impedance over here, the total impedance at this frequency is simply equal to R. So let me go ahead and write that. So the total impedance equals to R when omega equals to our resonant frequency. Okay, that means all we have then is only a resistive component to the total impedance. We no longer have these reactive components that are contributing, okay, to the circuit element. Okay, but it's really only at this specific frequency where this happens. But this is the resonant frequency. So now we can go back and calculate what the value is based on the value of the inductor and the capacitor in this circuit. Okay, so let's go ahead and do that. All right, again, now what we're going to do is just substitute the numbers here. I've given you values for this inductor and the capacitor. So we just substitute things in our formula over here. So here we have the square root of 200 milli, that's 10 to the negative 3. And then I need to multiply by the value of the capacitance, which in this case is 0.15 micro times 10 to the negative 6. Go ahead and put that in your calculator. Assuming that I've done things correctly, I get like 57, 70, roughly 74. Again, that's in kind of radians per second. You can convert that to hertz, pretty straightforward. Okay, so that's the value for this specific circuit. Again, what happens over here at resonance? This whole term goes to 0, okay? So that means that, what am I doing to the impedance for that value? Again, if you're at any other frequency, this term would contribute, which means you would be dividing by a bigger number. Okay, if you're dividing by a bigger number, you tend to make this impedance smaller. Okay, so really what happens over here is that this is really the maximum impedance you're going to get when you eliminate this term. And if I make the impedance maximum, okay, this becomes maximum at resonance because of the way the equation looks like, okay? And if that term is maximum at resonance, it means that the peak current is going to be a minimum when you have this specific frequency. Okay. All right, the next part is let's calculate the RMS current through each one of those branches over here. So this is kind of what we have, right? We're going to have some current here, might have some current here, and also, anyway, some current through this part. And again, what's going to be the total current kind of feeding all of these three branches right here. So in order to do this, let's kind of define a path here. And also what I'm going to assume here is that this power supply here, that the voltage is a function of time, is given by just a simple cosine function here, some amplitude, and multiplied by cos of omega t. Okay, so the first thing we would do is maybe let's define kind of different paths over here. This is path 1, path 2. And path 3. And if I start kind of over here, and again, what I'm basically doing is applying either a loop rule or kind of Faraday's law, whichever one you want to use. Again, through the resistor, it's pretty straightforward. We're going to call this, so for loop number 1, if I cross this power supply, I get a voltage across. And then I'm going to go down this center path. In the center path, I'm going to simply cross a resistor. So I'm going to get a voltage drop across that resistor as a function of time. And then I go back to the point where I started. So that's it for that one. That one's pretty straightforward. For path number 2, again, we're going to have a similar thing, minus the voltage across this other, the inductor. And you go back, and that has to be equal to 0. And for the third branch, again, so you start over here, and I'm going to do a complete loop going along the outer part of this circuit. So whatever voltage I gain here across this power supply, I'm going to get this voltage drop across a capacitor. Something like this. And this here must be equal to 0, right? And this basically says that the voltage across any parallel branch over here has to be the same. Okay, so this is kind of what we know. So let me just kind of rewrite this here. So we have voltage across the resistor must be equal to the voltage across the power supply. Our second equation here, voltage across the power supply is related to the voltage across this inductor. And also for the capacitor, the equation has to be something like this. All right, so this is a requirement. So we have our 3 equations over here. Let's now look at the current through each one of these segments. Okay, so let's start with the resistor. Okay, so for the resistor, here's our equation. Let's go down over here. All right, and V sub t is, I've given you what the equation is. It's my amplitude. So let's start with 1 prime prime over here. This is going to be the amplitude, V0 cos of omega t. And on the right-hand side here, we have the voltage drop across this resistor. Well, that's simply the value of the resistance multiplied by the current. And the current here is going to be a function of time. I'm going to call it I1, and I1's a function of time. So all we have to do now is simply divide through by the resistance, basically bring it on the other side. And now I have my expression for the current through that first branch of this parallel circuit, where you have V0 over the resistance. And all of this basically gets multiplied by the same time factor here, this cos of omega t. Which means that for this resistor, let's box this one in red. For the resistor, the current across that resistor has to be in phase with the voltage. Okay, and this is basically my expression. All right, let's now look at what's going on for the capacitor and also for the inductor. We want to find the current through each branch, and then we also want to find kind of the total current down over here. All right, so for the inductor, here's the equation here. And what I want to do now is, again, substitute on the left-hand side. We're going to have the same term, V naught cos of omega t. And now the voltage across the inductor you would write as, again, the value of the inductance multiplied by the change of current. And it's the current now through the second branch. So we're looking at this current with respect to time. All right, so just simply divide through by the induction over here. And what we have here is one expression, a differential equation, but that's okay. We'll solve this in a minute. V naught over L cos of omega t. Okay, so we're looking for a function, a current function, whose derivative gives me cos of omega t. All right, you can either integrate this both sides, or you can kind of take a guess. You know that these are related by sines and cosines, so let me just go ahead and kind of just write it out. I3, oh sorry, this should be I2. I2, that's the current in that second branch. I know that the derivative of a sine gives me a cos. And all I have to do is take care of this additional omega factor that's going to come out over here. So it's going to look like this. Sine of omega t. All right, and this you can check it out. You could substitute this expression kind of back into this one, take the derivative of this current relative to time, and you're going to see at the end you're going to get the same expression here on the right-hand side. All right, what I like to do actually at this point is use the fact that this is okay. What I really prefer, though, is to kind of rewrite this only in terms of cos. Okay. How would you write a sine in terms of a cos? You have to introduce a phase angle. And you might remember this guy. If not, it's kind of good to kind of review these things. But a sine of omega t, you can always write as a cos of omega t. And it's simply shifted by 90 degrees. Okay. Go ahead and kind of redraw both of these functions and make sure you understand this. Okay, why is it written like this? At the end, this is going to simplify our analysis. It's good to always write things, especially if I started out with a cos function as my driving voltage. I like to have everything else in terms of cos. And so let's go ahead and just do this final calculation. So the current through this center branch now is going to be written as something like this. So it's going to have some amplitude, which is everything here in the front of this trigonometric function. And then you get multiplied by cos of omega t and minus pi over 2. All right, so that's the current through the second branch. Let's now look at our capacitor, which somehow has vanished. All right, let's go back and now look at the current in the third branch. All right, so for the capacitor, one thing you should remember here is that the charge on the capacitor at any time has to be proportional to the voltage, and the constant of proportionality is the capacitance. All right, and the voltage across the capacitor, we'd write it as V subscript C. All right, our third equation that we had previously looks something like this, that the voltage across this power supply had to be equal to the voltage across the capacitor. So let's go ahead and use that equation and put it up here. That's going to help us. So we have that the charge as a function of time equals to the capacitance, and the voltage across the capacitor is simply equal to here. So V naught cos of omega t. Okay, my goal really is to find how much current is in this outer branch over here. Okay, well, the definition of the current there, let's call it I3 as a function of time. If you simply know how the charge is changing as a function of time on the capacitor, that basically is the definition of current. So all you have to do is differentiate the trigonometric function over here. The derivative of a cos gives me a negative sign, and you also have to use the chain rule and take out an omega. So it kind of looks like this. You have minus omega c v naught sine of omega t. Okay, again, this is fine. This is the solution. However, what I want to do now is use another trig identity and try to write this in terms of a cos. And that's just because my initial terms, my initial driving voltage, I wrote it in terms of a cosine function. It's going to help me later on in the analysis. So the identity I use in this case is that cos of omega t. If I shift it now in the opposite direction by 90 degrees, by pi over 2, this is actually equal to minus sine of omega t. All right, so here you can kind of group some of the terms here. Here's the negative, and here's the sine of omega t. So I can take those and replace it with my cos function. So my last kind of equation for the current in that capacitor branch should look like this. I get 3 terms in the front, right? Omega, C, and V0. That's going to be the amplitude of the current. And the time varying term over here looks like this. It's omega t, and in this case, it's plus pi over 2. Okay? Now, this tells me here that this current actually leads the voltage, right? The voltage is cos of omega t, and here I have plus 90 degrees, right? So this current actually leads the voltage by 90 degrees. All right, now let's put it all together. We know the current through each branch. What I want to do now is actually, let's find the total current going through this power supply. All right, we finish off question 2 now. Since we have all our expressions for the current, we're looking for RMS current. Okay, what I've given you here is RMS voltage. Now remember, any RMS value, let's just write this down. It could be RMS current or RMS voltage, is always the peak divided by root 2. Okay, so if you know the peak or if you know RMS, you can calculate what the peak is. All right, so let's go ahead and calculate what the peak is for each one of those. Let me go ahead and kind of make 2 columns here. Let's write peak and also RMS for each current. All right, so we have for the current I1, our peak value is simply V naught over R. Okay, and the peak value is going to be my 120 multiplied by root 2 and divided by 80 ohms. Okay, the peak, if I did that correctly, again, 2.12 amps. How about for the current I2? Again, the cos functions only vary between 1 and minus 1, so the peak is just everything in the front, right? For this inductor, we have V0 divided by omega L. Again, we have 120 root 2. Oops, apologize for that. And now 374, that's what I gave you for this angular frequency, and multiplied by the inductor, which is 200, multiplied by 10 to the negative 3 for my milli. Okay, so this current that I got was 2.27, if I did things correctly, amps. And the last one for this capacitor. The capacitor, on the other hand, again, it was equal to omega multiplied by C multiplied by the maximum voltage. So again, here you just substitute 374 multiplied by the capacitance, 0.15 times 10 to the negative 6, convert that to farads, and also times the maximum voltage. So here we get 120, which is RMS, multiplied by root 2. And if I did this correctly, I got something small, 9.52 times 10 to the negative 3. All right. Again, if you want to get RMS values over here, all you have to do is simply not include that root 2 factor. So it should be root 2 smaller, right? Go ahead and maybe include this. So any RMS current is related to the peak, and you simply divide by root 2 if you're dealing with just simple sine functions like this. All right, so that means for the current I1, I got 1.5 amps. For the current I2, I got 1.6, a little bit bigger. And for this one here, I think at the end I got 6.7 multiplied by 10 to the negative 3 amps. Okay, so the smallest one across this capacitor. All right, so I think that concludes kind of the second question. The next one is, what's the RMS current now delivered by the source? Okay, and there's kind of 2 approaches to do this one. Let's have a look at it. All right, so to look at the third problem over here is find the RMS current delivered by the source. I'm going to go back to a previous result where we found the impedance, right? And remember what we're doing here is we've basically simplified this network in terms of representing it with one total impedance, which we solve for, which means that I can write my expression as something like this, right? The maximum or the peak voltage is equal to the magnitude of the total impedance multiplied by the maximum peak current. And if I'm just looking for RMS current, again, the peak and RMS for simple sinusoidal currents are pretty straightforward, right? The RMS total current is going to be the total voltage across my equivalent impedance. So this is just going to be my 120 volts. That's what's given up here. And then divided by the magnitude of this total impedance of my network. Okay, and this is the expression I originally obtained. So what I did then, I just kind of plugged all these numbers into a Desmos. Let me kind of go show you how that was done over here. Let me open up a web browser. Here's the web browser over here. So we've got 374 as my angular frequency. My resistor was 80. Capacitance was 0.15 microfarad, 10 to the negative 6. Induction was 200 millihenries. And then I just substituted all of these numbers here into my calculator. And I got that the total impedance was approximately kind of 54.8 ohms. Okay, at the end, the RMS voltage was 120. And my current is simply 120 divided by my roughly 55 ohms. Okay, so at the end, you get like 2.19. Okay, so that's kind of the approach over here that I use. So the RMS current is approximately 2.19 amps. All right, great. And now the last one over here, let's look at whether or not the current is leading or lagging the voltage over here. And what that requires us to do is find what is the phase angle for this current. I'll show you how to do that. So the last part is let's find what the phase angle is. Okay, and really what we're doing here is we're trying to find this, which is I total. Okay, that's this guy over here. One thing we know is that this current, once it gets to this junction here, we can use Kirchhoff's current law over here, and that whatever current flows into the junction has to be the total current that's flowing out of the junction. Okay, so the current flowing in is actually what I'm going to call I total. So let's go ahead and write this, I total, and this is also going to be a function of time. This here must be equal to the sum of all three of those, right? You must have I1 plus I2, which is a function of time, and plus I3 is a function of time. Okay, now what you can do is you can substitute all these values now just to get one final function. Now it's going to look rather complicated, but we'll see how to simplify it in just a minute. All right, so this is what it looks like. So the first term is V naught divided by R and cos of omega t. Our second term now is V naught omega L, and again this is cos of omega t minus pi over 2, and then there's still this last term over here. Let me just write it over here, omega c V naught cos of omega t plus pi over 2. So we actually have three contributions. Okay, this first one actually is in phase with the voltage V of t. Remember, our V of t is right over here. All right, this is my V of t. And the first one is in phase with that component. This other one here lags by 90 degrees. The voltage across the capacitor over here, this one here is ahead by 90 degrees. All right, so what we're going to do now is really our goal at the end of the day is to write this as one function. Okay, it's to write it as I total, which is a function of time. We want to write this as one value, so our maximum current, which is basically what we just solved for. We found the RMS before, but you can find the max very, very simply. And it's going to be, again, another cosine function. However, it's going to introduce this phase. And this is really what we are looking for here, is what is this phase angle? If it's 0, it means that this total current is in phase with the voltage. If it's 90 degrees or negative 90 degrees, it might be some other value, some other angle in between plus 90 and negative 90. And so that's what we're going to try to solve for. And in order to do that, what we end up doing is we have to look at this equation and how do you simplify this equation in order to write it just in terms of one cosine function with the same angular frequency, however, only one angle. Okay, so let's go on the next page and we'll do that. We're going to use this concept of phasors in order to find this, and it's pretty straightforward. Okay, so this is kind of how, at least I would do it, I think. Again, I look at the current here. I'm drawing current now in the complex plane. Anything real has to do with resistors. The contributions from the reactive components like the inductor and capacitor gets plotted on the vertical axis, which is the imaginary component, or something that is out of phase by 90 degrees gets plotted on the y-axis over here. So anything that's in phase gets plotted as a vector here, and the magnitude of the vector is whatever the amplitude is, which we just calculated. So for our resistor, this is the current through the resistor, as I would write it as a vector that looks like this. And the magnitude of this vector is IR, which I know was V naught divided by R, like this. All right, the inductor now is, I go, well, it's omega t and minus pi over 2. It's minus 90 degrees. So minus 90 degrees means I rotate kind of in the clockwise direction. Let's go ahead and do that one in blue. So the amplitude you would write now for the current through the inductor, at least the amplitude I would write as something like this. And this vector here is what we're going to call, say, IL, the current, the maximum current through the inductor. This guy is V naught divided by omega L, and we solve for this. Right? We found that this vector over here, previously we solved that, which value is this? This was like 2.12 amps, if I recall. And the blue one was a little bit bigger. The amplitude was 2.27. And the capacitive component now, the capacitive component, if you look at it, it is plus, right? It's ahead. The current is ahead of the voltage by 90 degrees. So that one you would plot kind of along this axis. However, I'm going to make it pretty small because if you remember the current that we calculated for this one, this was the maximum current in that capacitor was omega c divided by V0. All right, so what you have to do now is we have to add all of these different contributions as vectors. Actually, my maximum current, you can see from here, the maximum current, the way you would do this now is, so you'd find the resulting component from the two reactive components, which is the capacitor and the inductor. And then at the end, you have to add that as a vector to the current through the resistor. And it ends up looking like this. So you get IR squared. Again, plus. Now it's the difference here between the inductor and the capacitor. And you have to square that term. And this is exactly what the previous expression was for my maximum current. What I'm now interested, however, is the phase angle. Right? My goal at the end was to write I total as some number. Some number I max and cos of omega t plus phi. So let's find what the angle phi is. Okay, again, if you would add all of these contributions as vectors, what I'm going to do here is let's just move kind of everything with the inductor. Let's move it on this side here just to give me a bit of space. So you first end up taking the difference between both of those vectors along this axis, which gives me, let's maybe do that one over here. Okay, so that's going to be something that's still going to be long, and this guy here is simply going to be IC minus IL. All right, it's going to end up being a negative value because we know that this 2.27 was much bigger than the current through the capacitor. And at the end now you have to add it to this resistive component. And then when you add it as a vector, you end up getting this guy over here. Okay, so this here is going to be, and the angle that we're really interested in here, this angle phi, is defined as this quantity over here. So at the end of the day, what this ends up looking like now is if I use tangent of phi, tangent of this angle phi equals to the opposite. The opposite now is IC minus IL and divided by IR. So now we can just substitute in all our magnitudes. Okay, IC minus IL. Okay, you can go ahead and evaluate this. What you end up getting is omega C V naught minus V naught omega L. And all of this now gets divided by IR, which was V naught over R. You notice you have V naughts in all the terms. You can kind of eliminate all of those. And I can bring this resistance into the numerator. Okay, and at the end, the final expression here I get for this angle tangent of phi, it looks something like this. It's the resistance multiplied by omega c minus 1 over omega L. Okay, so this is how you can find the expression. I can now substitute in all of the values that I have from the previous problem and obtain what the angle phi is. But clearly what you're going to see is should be a negative value. Okay, so it's not quite going to be negative 90 degrees. It's going to be something else. But let's go ahead and substitute and get what that value is. All right, so the last part I did was I just substituted in all the numbers inside my expression here for this phase angle phi, and I got negative 47 degrees. So that means that's the angle here that would kind of go into this expression. Now, if I was going to go plot what this current looks like now, here on this sketch over here, I've got the drive voltage, which is just a cosine function. So it starts at the maximum value at time 0 and just oscillates back and forth like a cosine does. If I want to now plot what the current looks like, again, it's going to be the same curve. It's just going to be shifted by negative 47 degrees, or shifted to the right by 47 degrees. So at the end, it would kind of look something like this. Oh, I'll try to do a little sketch. And again, this is the current. This is the total current going through that power supply as a function of time. Again, I'm plotting kind of current and voltage here on the same set of axes here, so there are different units for everything, but just so you get a sense of what it looks like here. And what that means here is that this current actually lags the voltage. Okay, this is what this angle means. Since it's a negative value, it behaves kind of like an inductor. Okay, and let me just write this down because it's kind of the important part. The current lags voltage by certain degrees, right? By 47 degrees approximately. Okay, and that you could see from this sketch, right? The voltage hits its peak. The current only hits its peak 47 degrees later in the cycle. All right, thanks for watching, folks. Hopefully you understood this problem. This is a kind of a difficult problem. It takes some time to digest. Work your way through it slowly and check all the algebra. Make sure you understand the steps. Leave a question if something you don't understand. I'll try to get back to you as quickly as possible.